All right, recall that we left off on Monday talking about hydrogen bonding. And we introduced the idea that there are these things that we call, unfortunately, hydrogen bonds, even though they're not actual bonds, or they're not nearly as strong as the other things we call bonds. Every year I try and come up with what might be a better name. How about extra strong dipole attractions because of positive hydrogen. So, Estaboff. So I'm going to try and use the word Estaboff instead of hydrogen bond. All right, so I'm gonna call these Estaboffs. Oh, Estaboff. Oops. That name is available if you want to name your child after hydrogen bonding. All right. So we mentioned that there are these especially strong dipole forces that we call hydrogen bond. So the question is why? What makes them different from typical dipole forces? So in this slide, I took two polar molecules, one involving hydrogen bonding and one not. All right, and I've drawn them in a specific orientation. So the first thing I want you to do is place your partial positive and partial negative charges around the atoms on these structures. All right. So it turns out hydrogen bonding is an interaction that occurs between the lone pair on one oxygen, nitrogen, or fluorine atom and the hydrogen on another molecule. Well, here I'm going to change that. So these are interactions between the lone pair on a nitrogen, oxygen, or fluorine and the partial positive charge on hydrogen. So I'm actually going to draw in my lone pairs on my oxygen over here. So this is why I drew this water molecule in the orientation I did. Because the two hydrogens would be pointed down like this so that my lone pairs would go up like this and over like that. Now similarly, if I draw my lone pairs on my atoms on the right, I have a lone pair here on phosphorus, and then I have lone pairs on fluorine. That I'm just kind of drawing in. Now, does anyone see a difference between these cases? Hydrogen does not have a lone pair. So, if you think about this hydrogen-oxygen covalent bond, the electron density in that hydrogen-oxygen covalent bond is all getting pulled over towards oxygen. So, when this other oxygen lone pair approaches, there's nothing there blocking its access to that positive charge. When you compare that with any other atom besides hydrogen, there are now lone pairs in the way. So on the right-hand side, there's a lone pair. So there may be some attraction between the phosphorus and the fluorine because of the partial charges, but it's not able to form as strong an interaction as it is in the case of hydrogen. So that's what makes hydrogen bonding, or S-Deboff, a unique phenomenon compared to other dipole forces. What questions do you have about that? Yep. So the question is, why do they call them hydrogen bonds if they're not bonds? Well, again, there's sort of an arbitrary distinction between a bond and not a bond. And the reason they call it hydrogen bonding is because it's relatively strong, and it's sort of in a specific direction because it's between the lone pair and the atom. And if you look at things in a deeper way, if you go into molecular orbital theory, there is some sharing of that lone pair with the hydrogen. So it is somewhat related to a covalent bond. The reason I'm so, I really want to distance it from the word bond is because it's so much weaker, right? Only about 5% as strong as a covalent bond typically. So it's much, much easier to break. And so that's why I like to have it as a separate, I like to think of it as a separate category. And I don't want you saying there are bonds between the molecules. If you want to refer to hydrogen bonds, you're more than welcome to, but you must say hydrogen bonds. Don't just say bonds. Okay? And if you want to say S-Deboff, you may. Just don't say it to anyone like outside of this class because they won't know what you mean. Like, don't write it on the AP test. But you could write it on my test. That would be fine. What else do you have? Okay. Because there are these two components to making esterbofs, we can have what we call the donor and the acceptor. So in this interaction, one molecule is providing the lone pair for the interaction, and one molecule is providing the partially positive hydrogen for the interaction. So we give those two things names. The H bond donor is the molecule that has the partially positive hydrogen atom as part of the interaction. And then a hydrogen bond acceptor would be the molecule whose lone pair is involved. Going back to the picture on the previous slide then, in this scenario, this molecule is acting as the hydrogen bond donor. And then the other molecule is acting as the hydrogen bond acceptor. So when we look at molecules, we can be explicit about whether it can act as a donor, whether it can act as an acceptor, or whether it can act as both. So to be a donor, what do you need to have? All right, so to be a donor, the molecule must have a very partially positive hydrogen. And what does that mean that hydrogen has to be bonded to? Yep. All right, so student question is, nitrogen and chlorine have very similar electronegativity values. So why would chlorine not get involved in this hydrogen bonding thing as well? And there is some question as to whether chlorine does hydrogen bond. Some sources will say yes, some sources will say no. Part of it has to do with orbital size. And when chlorine bonds to hydrogen, chlorine's a much bigger atom. And so it doesn't have as effective overlap with hydrogen's orbitals. So that affects the strength of the bond. It affects the polarity of the bond. and it also affects how well its lone pairs can interact with the hydrogen. So for more complicated reasons, we're going to just say chlorine doesn't do it. It's just these three. No. Yes, so the question is why nitrogen, oxygen, or fluorine? This is because they're the most electronegative. So they give hydrogen the biggest partial positive charge. The question is it possible to have more than one hydrogen bond between two molecules? Yes. But each one would have to have, if two molecules are going to make two hydrogen bonds, say, each one has to have a donor site and an acceptor site. You know, there have to be two separate donors and two separate acceptors within the molecules. So we'll look at some examples in a minute. Yep. The question is anything besides NO or F that can do this, and the answer is, for simplicity's sake, we're going to say no. While there might be some gray area, pretty much it's mostly a phenomenon of just nitrogen, oxygen, or fluorine. The question is, could we just make weaker hydrogen bonds with other elements? It's a good question. I'm not entirely sure. It may just be that they get so weak that we no longer remember. Hydrogen bonds are extra strong. So once we get below this threshold of being extra strong, then they just become regular dipole forces. And so, yeah, these three elements, nitrogen, oxygen, or fluorine, are strong enough, are electronegative enough that they seem to create a much stronger dipole force than any of the other elements. And if you think about it, there aren't a lot of nonmetals. So, and they drop off in electronegativity pretty quickly. By the time you get over to carbon, we're down to electronegativity of 2.5 from fluorine, which was 4.0. So, yeah, I'm glad people are bringing up the idea that there may be gray area and there may be other atoms that can sort of do the same thing, but it just turns out that only these three elements really make this happen. So I want you to just imagine that this is a special phenomenon for those three. All right, good. So next question is, because nitrogen, oxygen, and fluorine have different electronegativity, is there a difference in how strong the hydrogen bonds are? And the answer is yes. The more partially positive you make the hydrogen, the stronger the hydrogen bonding will be. And also, the better the hydrogen bond acceptor, the stronger the hydrogen bond will be. So there are varying degrees of strength of hydrogen bonds. We're not necessarily going to get into them so much. Because no matter what, when there's hydrogen bonding, it's much stronger than a typical dipole force. And so that'll manifest itself in different properties. All right, so to finish off this slide, hydrogen bond acceptors, what do they need to have? Daniel? They need to have a lone pair on a nitrogen, oxygen, or fluorine. So the next slide has 4 examples of molecules. For each one, I want you to identify whether you think it can be a donor, an acceptor, both, or neither. Okay. So my first molecule there might be familiar to you if you were a Breaking Bad fan. Anyone know what this molecule is called? Methylamine. Methylamine. All right, so Max, what did you guys say? Methylamine, can that be a donor? You said both. It can be a donor and an acceptor. Because it's got these partially positive hydrogens over here, and it's got a lone pair there. All right, good. Can be a donor and an acceptor. And you know what? I'm going to color code. All right. Danielle, what did you guys say for the second molecule? Both, all right. It's got lone pairs on oxygen. Those can act as an acceptor. And it's got this partially positive hydrogen over here that can act as a donor. One thing I want to note, these 3 hydrogens down at the bottom are the 3 hydrogens over on the left of the other molecule. Are those available for hydrogen bonding? No. So these and these are not available for S dub off. Okay. Well, those first 2 molecules, all right, can be donor and an acceptor. This third molecule, Daniel, you said acceptor. It's got lone pairs up on this oxygen. It's got lone pairs up on the oxygen where it can act as an acceptor. That nitrogen also has a lone pair. Someday when you take organic chemistry, you will learn that the nitrogen, actually its lone pair is kind of busy doing something else. So it can't accept hydrogen bonds there, but you don't really need to worry about that at this point. This molecule here is called DMF. It's a common organic solvent. And then the last one, Remy, what did you guys say for the last one? You said donor only, yeah. It was really hard for me to think of a molecule that could be a donor only and not an acceptor because it has to have a nitrogen, oxygen, or fluorine with no lone pairs. So this is pretty much the only thing I could think of that would be a donor only. But it's got 4 hydrogens available. All right, good. So let's look at some lovely hydrogen bonds in their natural habitat. All right. Lauren, can we kill the lights? All right, so here I have a sample of water. Water molecules moving all around, and I can ask it to show me the hydrogen bonds between them. The one green one is just an atom I clicked on. All right, so we can see in liquid water there are hydrogen bonds, lots of them between molecules. And hydrogen has this kind of unique position. Water has this unique position where it has 2 lone pairs and it has 2 hydrogen atoms. So it can act as a donor twice and it can act as an acceptor twice. So water is really set up for very, very efficient S-dub off. So most molecules in liquid water are going to be involved in 4 hydrogen bonds at once. If we look through this sample, most of them are. Sometimes they'll only be involved in 3 at a time, but most of the time they're involved in 4. Now, one thing I'll point out is in liquid water, because the molecules move around, you will see sometimes the hydrogen bonds break and then they form new ones. And so that's why I want you to think of these as different from covalent bonds, because in the water, the covalent bonds aren't just breaking and reforming that rapidly. Okay, they're much stronger. In ice, we can see the hydrogen bonds are actually really in a regular pattern. And if I let the water molecules move around in ice, that pattern stays pretty much intact. Okay? They jiggle in place, but they keep the same pattern of hydrogen bonding. Organic molecules like alcohols. Alcohols are molecules with an OH group. So alcohols are capable of making hydrogen bonds. If I go to my simplest alcohol, which would be CH3OH, we showed that on this slide here. So methanol is this second molecule here. Here's a model of methanol. And we can see methanol makes a bunch of hydrogen bonds. Not nearly as many as water, because it has those 3 hydrogens bonded to carbon that are not able to hydrogen bond. So the gray is the carbon and then the white is the hydrogen. You can see there's no hydrogen bonds to those 3 hydrogen atoms. If I look at bigger alcohols like ethanol, now there's even more carbon atoms. So there's even more hydrogen atoms that are not available for hydrogen bonding. So in a sample of ethanol, I see a lot fewer hydrogen bonds. I can look at even bigger ones like octanol. This will have 8 carbon atoms. And now in this whole sample, I only see 3 or 4 hydrogen bonds because there's so many hydrogens that aren't available. So that's going to explain differences in properties. Even though these molecules are capable of hydrogen bonding, the more of those carbon atoms you add in, the actually less important the hydrogen bonding becomes, because it's only a small part of the molecule that can actually do it. Here is sugar. So if you take table sugar, a molecule of table sugar looks like this. And change it. So here's a model of a molecule of table sugar. Red is oxygen, so you see there's lots of oxygen to hydrogen bonds. And so in solid table sugar, there are lots and lots of hydrogen bonds. Now, what happens if you spill sugar on the floor and then step on that same floor a little later? Or if you spill like soda on the floor? It's sticky. Why is it so sticky? Hydrogen bonds. Yeah. Because those molecules make a ton of hydrogen bonds, which means they stick together very well. And then they'll stick to other things that make hydrogen bonds really well. So the question is, does that mean your skin makes hydrogen bonds? Absolutely. I mean, we are mostly water, right? So we can make, we make lots of hydrogen bonds. Now, our skin is coated with a little bit of oil, right? Which is nonpolar, which is why, water doesn't just immediately soak right into us. You take a shower, you don't become bloated, because we do have a layer that the water doesn't hydrogen bond with, but yeah. If I look at a fatty acids are these long carbon-hydrogen chains, and then they have a carboxylic acid group at one end. So again, if I have a sample of a fatty acid, there's a few hydrogen bonds, but mostly it's just these nonpolar parts of the molecule interacting. And now let's go to some biomolecules. So hydrogen bonds are hugely important to us biologically because they keep all of the molecules that make us, they keep them in the right shape. So if I look at DNA, all right, here's a model of DNA. Double helix. Maybe I can change the model type. All right, so here's my double helix of DNA. And what do you see holding the two strands together right in the middle? Estobofs. Yes. You can see the reason that the letters of DNA are actually different chemical structures, but the reason that they know which one to pair up with is that they make a certain number of hydrogen bonds in a specific arrangement. So one set of the DNA letters makes 2 hydrogen bonds between it, and then the other kind makes 3. So here, down here, there's 3. I forget which is A and G and T and C, but and then here there's 2 hydrogen bonds. So hydrogen bonds hold DNA together. It's important that hydrogen bonds are strong enough to keep it in that structure, but also weak enough that when you need to open DNA to get the information out of it or to copy it, that you can do that. You don't have to break covalent bonds to open up DNA, just hydrogen bonds. So that's why hydrogen bonds are a great choice, because they're strong enough but not too strong. Proteins like insulin, you may or may not know, proteins have to have a very specific shape in order to do their job. And they're these big long molecules that have to fold up in a certain way. One of the things that makes them fold up in that specific way is hydrogen bonds. So if I take this model of insulin and I decide to show the hydrogen bonds, we'll see there's a bunch of hydrogen bonds in critical places holding this in its shape. Same is going to be true if I look at hemoglobin, which is a huge molecule. So there's hemoglobin. Those big spheres there are iron ions. That's the part that oxygen attaches to carry the oxygen around your bloodstream to all your cells, are those iron ions. And there are lots and lots of hydrogen bonds making sure that this stays in just the right shape. And guess what? If you're missing one of those hydrogen bonds, it could cause the whole shape to be thrown off, and you can get diseases like sickle cell anemia, where hemoglobin just doesn't have quite the right shape, and it can drastically alter people's lives. So the student question is, why are there so few iron ions? Well, there's 4 of them in this molecule, and I don't know. That's the number that nature came up with for our hemoglobin molecules. So the question is, if you added more, could you breathe less? Well, here's the thing. Every system in our body has evolved together, right? So if you decided at this point, wait, I want to change hemoglobin to make it more efficient, I'm going to add more iron to it, well, all the other systems in your body aren't going to be able to use it anymore. So like I said, one little change in the shape can make this molecule no longer function properly. So at this point, we can't necessarily just mess around with it and say, let's add more iron ions. Question is that eventually something we'd be able to do? I don't know. I seriously doubt it. Evolution was a very long process, and there are certain things we can redesign, but I don't expect that we can actually just redesign a molecule this complicated. But there are things you can do to make your body more efficient at using oxygen, like training at altitude or living at altitude. And yeah. But as far as just altering the molecules, I think it's too complicated a system. So coming up with artificial biomolecules, I don't know. People work on things like that. So maybe. All right, so the point is hydrogen bonds are important. In biomolecules, they hold proteins in the right shape. Well, there we go again. Estaboffs. They hold proteins in the correct shape. They allow DNA strands to stick together. Among many other important things. So they do a lot. They're important to us. All right, so far we've dealt with how ions are attracted to each other, how polar molecules are attracted to each other, how ions and polar molecules are attracted to each other, how polar molecules and nonpolar things are attracted to each other. There's just one thing we've left out, and that's what if I have just nonpolar molecules? How are they attracted to each other? And it turns out this is going to be kind of a hand-wavy argument. But we say there are attractive forces between them. We know that because we observe it. And what we call them are dispersion forces. And the way we rationalize dispersion forces is by saying random motion of electrons can cause this fleeting attraction between them. All right? So here's the way I think of dispersion forces. Imagine a nonpolar molecule at a random moment in time. You may start out with a perfect sphere of electron density, and in your notes this is an actual circle on the left. I know on screen it's more of an oval. But at any moment in time, the electrons might happen to be on one side. And so it might be somewhat polar for an instant. Question? Okay, so the question is, why are the electrons moving? And the answer is, electrons are always moving. Everything always has some thermal energy. Even at absolute zero, electrons don't stop moving. They have some minimum of energy. But at room temperature, everything has lots of thermal energy. So things are all constantly moving, including the electrons in the electron cloud around an atom. So at some random instant, we have kind of this momentary dipole with a partial positive on one end and a partial negative on the other. The question is, I'm saying this like I'm not really sure of it. And my response is, that's true. Like everything else I say in this class, I'm discussing models that I use to think about specific situations. I don't necessarily think about them as the truth. So this is my model for thinking about dispersion forces. There may be other ways to explain it using other models. Oh, and I wrote down there random dipole. All right. So if that random dipole approaches another nonpolar molecule, just like we saw with dipole-induced dipole forces, it's going to cause the electron cloud on the other molecule to move to one side. So now I have two sort of dipoles next to each other. So we talked earlier about dipole-induced dipole attraction. This is really random dipole-induced dipole attraction. Joel? Oh, the question is, do you want to see my great animation again? Here it comes. Oh, the question is, can we see this on a microscope? Nope. I mean, atoms and molecules are too small to see under a microscope. There are some molecules that are big enough that you can see them under a microscope, big macromolecules with lots and lots of atoms. But anything we're talking about, and this is why I talk in terms of models, anything we're talking about is too small to actually see. And while we do have things that we call microscopes nowadays that can that can generate images of atoms, they're not actual microscopes because they're not actually using light to see things. They have to see things in a different way. So when you hear about electron microscopes or scanning tunneling microscopes or atomic force microscopes, they're not actual microscopes in the sense that light bounces off things and bounces back and we see it. Yeah, so the question is, how do electrons move to one side because they're in their specific orbitals? Remember about orbitals, the orbitals are spread out over the whole atom. And the electron is not at a defined position at any point in time inside it. So, yeah, like I said, this is going to be kind of a hand-wavy discussion, and really I just think of the electrons as being free to move anywhere in that cloud. And when two molecules get near each other, if both of those clouds happen to move to one side, they cause this attraction between the two molecules. And the whole result is that we get this really weak attraction because it's this fleeting random motion of electrons thing. Now, the thing about dispersion forces is they're always present. There are dispersion forces between water molecules. But between water molecules, the dispersion forces get dwarfed by the hydrogen bonds, which are much stronger. So we only usually are concerned about dispersion forces with nonpolar molecules. And dispersion forces will be present all along the surface of any two molecules. So anywhere where their surfaces come near each other, there's potential for dispersion forces. So as a molecule gets bigger and it has more surface, dispersion forces become more important. All right, so let's do a little summing up. We've talked about a bunch of different forces that we can have between particles. So let's just make a list of the different forces so that we can put them in order. What are they? All right. All right. So we talked about those 6. And last time we had put the first 4 that we had discussed in order. So now it's just a matter of, all right, where do dispersion forces and Esteban fit in? So strongest ion-ion because full charges. Second, ion dipole. Full charge, partial charge. Third, Esteban. Fourth, dipole-dipole. Fifth, dipole-induced dipole. And last, dispersion. And I want to point out one more thing before we run off, and that's some of these can be present in pure substances. Some can only be present in mixtures. So the ones with the red star here, these can be present in pure substances. The other two, because they involve two different kinds of things, are only present in mixtures. So maybe I'll these are only present in mixtures. All right.